Good morning, everyone. My name is Juliana Martel, and I am a marine biology major as well as a geoinformatics minor. And today I am presenting to you remotely via this recording because unfortunately I am not able to be there during presentations. That being said, let's just jump right into it. I want to try to really speed through this. All right, so my research is using precipitation data as a proxy for total suspended solids in chlorophyll-a concentrations in the US Virgin Islands. And that's kind of a mouthful, but it explains exactly what I'm doing. I'm going to jump in and zoom in to my introduction and study area. And if you would like to read along, I'm going to zoom into every section, but I'm going to try to give like a really consolidated, quick blurb on each section. All right, so coral health is super important for many different environmental and cultural reasons, but because of anthropogenic effects such as increased watershed or climate change, coral health is a little bit vulnerable. Watershed is basically when it rains, a bunch of like loose sediment or plant matter will kind of come down the side of the island and into the water. And this watershed can alter different water quality parameters, such as total suspended solids and chlorophyll-a. And chlorophyll-a is a really useful biomass indicator for phytoplankton. So just in your mind, when I say chlorophyll-a, think about phytoplankton biomass. All right, so it's super important to measure these specific water quality parameters because of their impact on coral health. Um, but it's kind of difficult sometimes to go out and sample all the time. So these models are super helpful for kind of remote sensing. In this research, I'm going to try to see if I can use precipitation data to create accurate predictive models of both chlorophyll-a and total suspended solid concentrations at coral monitoring sites on St. Thomas. So this is the 13 different sites that I visited to collect the chlorophyll and TSS data. And I'd also like to point your attention to this topographic map on the top and watershed map on the bottom. And I just kind of want you to keep in mind that this portion of the island is the steepest when we look later at the classification maps, and that the watershed zones kind of match the topography, if you can see. All right, move on to our next portion, and that is our methods section. First, I'm going to talk about the data acquisition. So, like I said before, the chlorophyll and TSS data was collected in situ from these 13 different coral monitoring sites. I have two pictures on the side of what the filtration and fluorometron, oh my God, fluorometrical, basically the way that we estimate chlorophyll. But yeah, and then the precipitation data I collected from two online data portals, one which is a volunteer-based system, and that's the Community Collaborative Rain, Hail, Snow, and Network data data viewer, as well as a official kind of government source, NOAA's National Weather Service now data portal. All right. So here we have my methods, processing, correlation, and regression section. And you can follow along to this text, but essentially this figure explains what I'm doing. So I clean up both the chlorophyll TSS and precipitation data, but it's kind of hard to merge them together because we have basically a set of precipitation stations and coral monitoring sites that we need to link together based on what site is closest to what station. And I did that by using the coordinates of both the monitoring sites and the precipitation stations. And I used SciPy, let's see if I can see it, SciPy spatial CKDT tree, which is kind of like a clustering method. I believe it stands for compressed K-dimensional tree, whatever. What I did is I basically found the nearest neighbor for each site, the nearest station neighbors, and I have three columns here, the nearest station, and then I linked the chlorophyll TSS data with the precipitation data, making sure that it only links each site, so such as like Flat Key, only links to the stations that are nearest. Then I took the average of those three stations, and now we have our final data frame that I used to do all of my modeling, correlation, and regression stuff there. All of that I did with these specific methods from these libraries you can see towards the end. And I also created a few classification maps. So before we jump into the modeling and correlation results, I want to look at the classification results. So this is the distribution of all of the chlorophyll, sediment, and organic matter data on the top here. And then on the bottom, it's the average per site. And I split it into three portions. And you can take your own time to look at the figure descriptions. But basically what I'm saying is that of the three bars for each chlorophyll, sediment, and organic matter, the one on the left is considered like low, and then medium, and then high. And then that helped create these kind of classified average chlorophyll and classified average TSS maps. And I'm gonna move this over here. But in the top left corner, you can see the topographic map, and on the bottom right corner, you can see the classified maps. And what I'd like to say is that the highest concentration of specifically chlorophyll tends to be centered around those high topographic areas, and that's areas that might maybe experience more watershed. All right, and so now I have my, oh, okay, our correlation and model results. So the three graphs you see here are the correlation between the precipitation data and the sediment and organics data. Oh, and if I didn't make this clear, when we look at chlorophyll and TSS or total suspended solids include inorganic sediments, inorganic solids such as sediments, as well as organic solids. And so I split that up into sediments and organics, but unfortunately, precipitation versus chlorophyll and precipitation versus sediments ended up not being that strongly correlated to each other. You can see chlorophyll is almost there with a p-value of 0.06, but we can see that organics are definitely correlated to precipitation with a p-value of 0.001. And that's kind of reflected in the linear regression model. So right below each graph, you can see the model performance. And we can see that the chlorophyll and sediment models ended up performing like they basically failed, but the organic matter model actually ended up doing pretty good. It could explain 67% of the data, and it has a relatively good RMSE of 0.92. And so now I have my discussions, conclusions, and ethical considerations. Again, you could read along if you would like. I basically relay the results. And what I would like to say is that one limitation I had, unfortunately, was the limitation of precipitation data. There wasn't that much of it, and I would have liked to have more data points because it ended up happening that there was way more chlorophyll data or way more TSS data and not enough precipitation to kind of do really good stats. So I think if I had a little bit more precipitation data, maybe we could strengthen that organic matter model and maybe even find an actual correlation between chlorophyll and precipitation. Lastly, I just have figure descriptions and my citations. This is the poster on a big scale, and I also have my QR code for the project drive. All right, thank you. Unfortunately, I can't answer any questions, but I hope all of you do really good on your presentations, and I'm sure you will. Thank you.